next bit then. So this is the moments question. You've got the pivot here, and you've got two forces labelled, and there is a third force. There must be a third force. If there wasn't another force, this whole thing, this meter ruler, would actually physically be moving in an anti-clockwise direction. Well, the reason it isn't is because of this spring here, this attachment, and there's a force there, F, due to the tension in the spring. Now, before you can do this, you need to work that out, and the way you work that out is using F equals K times X. So there's K, and X is the extension. So, and here's where some of you mess up. You haven't read the whole of the question. The new length of the spring is 17 centimetres. The original length is 10 centimetres. So the extension is 17 minus 10, which is 7 centimetres. Okay. Right. So now we need to use the principle of moments to find a value for X. This is a different X now. We've used X up there for extension. This is that missing distance. Okay, so let's just see. We've got those two forces labelled. That's a distance we don't know. We're going to need this distance. Oh, and we've got the distance for that force, because remember, moment is equal to force times perpendicular distance from the pivot. So what's this? Well, we've got 1.2, which is the weight. Where does the weight act on a meter ruler if it's uniform? And it says it's uniform. Look, it acts at the middle, right? So I know that's 90 centimetres, but the whole length of the thing is a metre. So that there's going to be 50 centimetres. All right. Okay, so principle of moments says that the sum of the anti-clockwise moments must be equal to the sum of the clockwise moments. The anti-clockwise moments must be equal to the clockwise moments. Okay. Oh, let's work this force out first of all, shall we? Force equals K, which is 20, times the extension, which is 7 centimetres. 7 centimetres is no use. We need to turn that into metres, right? Don't forget, it's all here for you. Centimetres times 10 to the minus 2, that's all you've got to do. So we've got, where's my calculator? 20 times 7 times 10 to the minus 2 is 1.4 newtons. Does that look like a sensible number of newtons? Yes. All right, so anti-clockwise forces that would tend to give you an anti-clockwise moment are this one and this one. So it is 3.0 times the perpendicular distance, which is our missing X, plus the other anti-clockwise one is the 1.2, and times the perpendicular distance, which is 50 centimetres. I'm going to turn this into metres, I think. And then the clockwise one, the only one that would tend to be making it go clockwise is F. So that is 1.4 times the perpendicular distance there, which is 0.90, again turned into metres. Okay, so quickly then, multiplying through the brackets, so I'm just going to call that 3x plus 1.2 times 0.50, which is 0.6, equals, and that is 1.26. So then we rearrange this, collect like terms, so it's 3x equals 1.26 minus 0.6, which comes to 0.66, and x is 0.22 metres. And if you look at it, does that seem like a sensible value? 22 centimetres, yes it does. Okay, last bit on this question then. We've now got two springs of the same type 2 springs of the same type, it says. That means, if they're of the same type, that means that the spring constant for one of them is 20. You know, that means you have to put 20 newtons on there to get 1 metre of extension. So those 2 springs are in series. In series, when you put 2 springs in series, they will be a lot more stretchy, right? They will be half. Spring constant is the stiffness. If you put 2 in series, they will be half as stiff, right? 2 springs in series, stiffness will be half. Therefore, the spring constant will be half. What's half of 20? 10 newtons per metre. So who's correct? It said is 40. Laura said, so Laura is correct. Okay.